In this video, we're going to be talking about the factors that affect the speed of a wave. What we're going to do, we're going to look how we can calculate both the translational speed of a wave and the average speed of the particles that make up that wave. We'll also look at the differences, again, between a transverse and longitudinal waves. We're going to look at various properties of the wave, such as period, frequency, wavelength, and amplitude. We've talked about them a little bit before, and we're going to review those again and apply them to the speed of a wave. We're also going to look at what affects the speed of a wave and how it compares to physical objects. Why are we doing this? Because even though waves are different from physical objects, the definition and meaning of average speed and velocities are the same regardless of what you're looking at. Waves are also a system of complex motions of individual particles that we simplify down to what we call a simple wave pattern. And to really understand waves, we have to understand how those particles move. The concepts of frequency and period are huge in waves, and so we really need to understand what they are and be able to define them and recognize their definitions and apply, most importantly, apply those definitions. And even though waves themselves are not actually physical concepts, and so they aren't governed by the physical laws such as Newton's laws of motion, the particles that make them up are in fact governed by the laws of motion. And so to understand how the whole illusion moves and the properties of that illusion that we call a wave, we need to understand how the particles are affected by the laws of motion. So here we have a longitudinal wave, also known as a compression wave, and we've seen this before, where we have our particles that move forward and backward in the direction of the line of the motion of the wave. The materials actually compress into tight regions that we can track. And if we watch the individual particles, we can see how the individual particles are actually just moving forward and backward. So again, just like we had talked in the past, if my particles move in the same and opposite direction as the wave, we have a compression wave. However, a transverse wave, like a water wave, the particles move perpendicular to the wave. So as the wave is moving in this direction, the particles move up and down. Or if the wave is moving this way, the particles then would be moving right and left. It's not that the particles move up and down, it's moved that they are perpendicular to the motion of the wave itself. When we compare these two waves side by side, we can see that they have some very common properties, although they are different. We have a wavelength that is going to be from the top of a wave to the top of a wave, which is the same as a compression to a compression. Remember, compressions are the points of the matter where they are closest together, they are most compressed. The point on where they are most spread out is called a rarefaction. When we look at transverse waves, we can often think of the top of the wave as being a compression and the very bottom of the wave being the rarefaction. They are not the same thing, but they are analogous to one another. A wavelength, the length of the wave, is defined as the distance between two peaks of a transverse wave, peak being the highest point possible, or from a compression to a compression, which is equivalent to a peak. We could also view it as the bottom of the wave to the bottom of the wave, which is called a trough, named after a feeding trough, actually, or which would be the same thing as a rarefaction to a rarefaction. We don't like dealing with rarefactions for compression waves because, again, it's hard to spot those. The compressions, at least, are very dense, and we can kind of see where it's the most compact, where it's the most spread out is very hard to see. So we very rarely ever deal with rarefactions when dealing with compression waves. However, for a transverse wave, we can either use peaks or troughs. It really doesn't matter. But just like with transverse of the compression waves, we like working with the peaks because they're more like the compression. but a wavelength really just means the length of a wave. The size of the wave is a hard thing to describe because waves actually have two sizes. We have the length of the wave, and we also have the maximum distance that the particles have moved from the middle of the wave. The maximum distance that the particles move is called amplitude. That has nothing to do with the wave length. The length of the wave is the distance between one crest to another. It's the distance a wave has to travel to complete one cycle. Amplitude is just the distance that the individual particles have to move. The amplitude above and below a wave are always symmetrical. Another thing that we've talked about in the past is frequency. When something happens frequently, it means it happens often. Frequency is just a measure of how often something occurs. We have always defined frequency as the number of cycles, vibrations, events that take place in a given amount of time. So frequency is just the number of cycles that take place. So if I have a guitar string that vibrates back and forth, a frequency would be the number of times it goes up and down, up and down, up and down, up in so many seconds. The unit for frequency that we often use would be either like 1 per year, 1 per day, 1 per second. The most common one we're going to work with waves will be the 1 per second, which is also called a hertz. Period is the time it takes for a cycle to complete itself. So every time we deal with period, it's actually like a period of time. For example, your school is broken up into 7 periods. Theoretically, each period is the same amount of length before the cycle repeats itself. And so we use that term as a period. If you play hockey or watch hockey, hockey is broken up into 3 periods. And again, each period is the same old length of playing time. So if I have a clock, the period is the time it takes to swing back and all the way forth. So the time for a tick and tock is a period. For a wave, it would be the time it takes to go from one crest all the way down to a trough and back up to the crest. It's the time to produce one wavelength, which would be one wave. Period and frequency are inverses of one another. Period is the amount of time per cycle, and frequency is the number of cycles per time. This is not a basic equation, it's a fundamental relationship. But anytime you give me period, I automatically know frequency, because if the period is 10 seconds, my frequency must be 1/10, because it takes 10 seconds to make one wave, so I can only produce 1/10 of a wave in 1 second of time. If I was to make a graph of a particle's position with respect to time, I can see the longer the time, the longer the period, but I get a lot less waves than if I have them in shorter periods of time. So again, long periods have low frequencies and short periods have high frequencies, because again, period is the inverse of the frequency. So as one gets bigger, the other must get smaller. When a wave travels, it can only travel one wavelength in one period. So if I wanted to find the speed of a wave, and speed is always distance over time, the distance the wave travels is one wavelength. The time would be one period. So the speed of a wave is really just one wavelength per period. If I had 5 wavelengths, it would take 5 periods, which would reduce back down to one wavelength per period. But 1 over period is also frequency, and it's much more convenient to deal with frequency than periods in most cases. So we can rewrite the speed of a wave by replacing divide by period with multiply by frequency. So the speed of a wave is often calculated by wavelength times frequency. This is actually a base equation. We will not need to have it memorized. It will be given, but it only works for waves. And even though it doesn't look it, it truly is distance over time, because that is the definition of speed. If I take a look at how we can calculate the speed of a wave, we can turn around and say it's really wavelength times frequency, which is the same thing as if a person was walking. If a person walks with a frequency of 5 steps per second, and they have a stride length of, let's say, 2 feet, then their speed would be 10 feet per second, because they are making 5 steps every second, each one being 2 feet, meaning it would travel 10 feet per second, which is really fast. Likewise, if I have a wheel that is spinning, we have our circumference over the period for one rotation. But that would be the same thing then as my circumference times my period. Oh, sorry, circumference times my frequency. Because if I have a circumference of, let's say, 2 meters, and I rotate in 2 seconds, then every second I go through 2 rotations, each one being 2 meters, so I go 4 meters in 1 second. So again, distance over time and repeated length times frequency are really the same thing. One of the things that often will confuse people is the concept of a reflection or an echo. The speed of a wave is always the distance traveled over time, but if I'm hearing an echo, the wave travels out to an object and then goes all the way back. This means that the wave travels not the distance to the wall, but double the distance. So the speed of wave would be double the distance of the wall divided by the time I hear for the echo. The time I hear for the echo would be the time it takes for the sound to go all the way back and forward. If I want to calculate the speed of the particle, however, that's moving back and forth that makes the wave, that would also be the distance traveled per time, but not the distance of the wave, but the distance of the actual particle that travels. And a particle, starting at amplitude, would drive down to equilibrium, then drive down 1 amplitude to reach the bottom. To return back up, it would travel double the amplitude again. So a particle in one wave cycle always travels 4 times the amplitude. That would happen in one period. So a particle's average speed is always 4 times the amplitude divided by the period, which is also the same thing as 4 times the amplitude times the frequency. Wavelength has nothing to do with the particle speed, because there is no wave really. It's just an illusion of all the particles moving back and forth. If I take a look at the speed properties of a wave versus a particle, I can see that they are very different from one another. Wave speed is a constant, so we never really call it an average, even though it is always an average. It's nothing physical, it's only the motion of energy. It is distance over time, and it depends on the medium. Sound waves travel faster in water than they do air. Sound waves travel faster in ground or solids than they do liquids. That's because the molecules are able to vibrate much more rigidly in a solid than it does in a gas. There is absolutely no relationship between the speed of a wave and amplitude. It has only to do with the material that's traveling through. It actually has no relationship with wavelength, even though the equation kind of shows that. It also has no relationship with frequency or period. It only moves in one direction. This is very confusing for people because when I look at the equation, I think it does. But my speed is a constant. As I change my frequency, my wavelength also changes. Particles don't have a constant speed. They're always speeding up and slowing down and changing direction. They are actually physical objects that are carrying the energy, so they're governed by Newton's laws. The definition of speed is distance over time. It does depend on the material, because the more rigid the material, the faster we're going to move up and down. It does depend on amplitude, but not wavelength. It does depend on frequency. It does depend on period. And it has no relationship with wavelength whatsoever. And it moves in 2 directions, because particles are going to move up and down or forward and back. We can set up a Venn diagram of the exact same list, and we can see that the only thing that wave motion, particle motion have in common is that it's distance over time, and they both depend on the medium. Those are the only properties that they actually have in common. The speed of a wave depends solely upon the material and nothing else. This is very misleading when we look at the equation, because when I get asked a question such as, if I double the frequency, what happens to the speed? I would think, well, if I double my frequency, my speed should get bigger. But if I double my frequency, the time it takes to make a wave is now half of what it was. That means I can only make a wave half as big as before. So if I double my frequency, my wavelength has to get smaller by 1/2. So if I double one and half the other, the velocity does not actually change. This is not the equation where y equals some constant times x. This is actually an equation where a constant equals y times x. A little visual that you can use to help yourself is a little seesaw. where I have period and wavelength on one side, frequency on the other, and my speed is in the middle. And this works exactly like a seesaw, where if my frequency was to go down, these other two guys would go up, so my period would increase, and so would my wavelength. My velocity, however, in the middle stays exactly where it is. Likewise, if my frequency was to increase, this side would go down, so my period and wavelength would actually get smaller, but the speed of the wave actually remains constant because I haven't changed the material that the wave is traveling through. I hope this helps clarify some stuff about the speed of a wave. If you have any questions on it, do not hesitate to give me a holler. I'll be more than happy to help you guys out.